So today I'm going to talk about the solution of ordinary differential equations in Python using the scipy function ODE And so let's get started by just importing some libraries. So we're going to import numpy as np. We're going to import matplotlib, pyplot as plt, and then that's for our plotting. And then from scipy integrate, we're going to import ODEInt. And so that's going to be kind of the core function is ODEInt. It's going to have a similar format to the root command. But just to show you what we're going to try to solve. So basically, I'm going to just do this in Markdown. So we're going to do frac dx dt is equal to f of x comma t. And then we're going to have, put some space, x of 0 is equal to some initial condition. So what we're again trying to solve is dx dt is equal to f of x of t. So this is the right-hand side, which is a function both of x and t. And then we're going to have an initial condition, x of 0 equals x naught. So I'll show you a little bit. X doesn't have to be a scalar. It can be a vector. So we'll do vector value functions in a bit. But let's just start out with something really simple. So let's do dx dt is equal to minus 3x. And then maybe x of 0 is equal to 1. And so this is a relatively straightforward function to solve. So we can define x of t, which is our right-hand side. In this case, it's solely a function of x. So even though we have the t part here, it doesn't need to be the function with the t part. So we can just do minus 3 times x. Then we do our initial condition. Let's set it equal to 1. And then we define the range of solutions that we want to look at. And so we want to solve this from 0 to 10 units with, let's say, 100 data points. And so we're just going to say, x is equal to ODEInt of f, x naught, and t. So again, we have our right-hand side, our initial condition, and basically the times we want to run the solution. So I always run this first and make sure I don't get an error. And that's good. So then we can plot it up. So we can do plt, t comma x, let's do line width equals 3, and then color is equal to red, and then plt show. And we have basically a first order system here, decaying from 1, and then it's going to decay to 0. This solution here has an analytic solution. So if I come back here, x of t is equal to basically exponential minus 3t. All right, so that's the analytic solution. So I could also plot up plt plot t, and then I could do exponential of minus 3 times t, and then let's do line width. Where did I go? Line width equal to 3, and color is equal to blue. And I run it, and you see that both of these solutions have exactly the same solution. And so in general, these differential equation solvers are pretty robust and give you fairly accurate solutions. Typically, in all honesty, when I try to analytically solve a differential equation, I typically just first numerically solve it, and then I'll try matching my analytic solution to the numerical solution, because I tend to trust my numerical solution more than I do my analytic solution, because I can make lots of mistakes with the analytic solution, particularly if it's something more complicated than a simple linear first order differential equation. So we can do more complicated expressions. So maybe we could do dx dt is equal to minus x, and then maybe we'll do cosine of t, and then x of 0. In this case, let's just do a 0 initial condition. So we can define f. Here's x comma t. And then we're just going to return minus x plus np cosine of t. And then x of 0 is equal to 0. T is, in this case, let's do 0 to 20. And let's graph 500 points. And then x is equal to ODEInt f, x naught, and t. And then we can plot x, t comma x, line width equals 3, color equals red. And then we can just do plt show. And in this case, if you look at the solution, we have, because there's a cosine here, our solution is going to oscillate. If we wanted to run it a little bit longer, so maybe we'll take it out to 200 time points, you're going to get lots of different oscillations with that solution. So that's kind of the general overview for at least a one-dimensional basically differential equation, but we can also do multiple dimension ones. And so let's maybe do dx dt is maybe minus y, and then we can do dy dt is equal to positive x, and let's say x of 0 is equal to 1, and y of 0 is equal to 0. I think this one should oscillate, but let's just find out in a second. So in this case, we're going to have x and z coming in. So basically in the solution, just like in the root command, let me get this right. Oh, keep on doing it wrong. Z is going to be the vector x comma y. So we're going to store our information of x comma y in the vector. So the easiest way to do this is we can unpack x and y from z, and then we're just going to return our first function, which is going to be minus y, and our second function, which is going to be x. Our initial condition, z naught, in this case is going to be 1 comma 0, and maybe we'll do we'll look at the first 20 seconds of the solution. So I'll do 1,000 points. And so I do x is equal to OD in f z naught and t. I run it, make sure everything's right. And now if I want to plot it up, let me clean this up. So that's z. So the way it works is, let me just shorten this one down, and let's assume we do 10 time points. So if I print z here, what I'm going to get back is 2 columns. So this is kind of a Python representation of a matrix, right, which is a list of list elements. But in our case, the first column, so this column right here, is going to represent x, right? And then the second column is going to represent y. If we had a third variable for the differential equation, that would be the third column. And so if I just show this, if I want to access, say, this element right here, right? So when I'm looking at this, is the way we count is the first index is the row number, so it's 0, 1, 2, right? So we can put a 2 there. And because it's a NumPy array, we don't actually have to do bracket and bracket. We can just put a comma. And then if I want the first element, I would put 0. And I'm going to get back that first element, which is minus 0.264. And that's minus 0.264. Now, if I wanted the full column, I could just do tilde, right, which is telling me I want all the rows, and then 0 tells me I want the first column. So that's going to be the first column. And if I run this, I actually get back that first column. So I get 1, right, minus 606, minus 606, and then I have minus 2.64, minus 9.7. So that's going to be kind of my first column. If I want to look at the second column, I'm just going to put 1 there for the second column. And I'm going to have the values for the second column. So this kind of nomenclature is very similar to MATLAB, if anyone's used it, right? So this is telling us to grab all the rows, and then 1 is grabbing the second column. You know, I could always flip it. You know, if I wanted the second row and all the columns, I would do 2. The third row and all the columns, I do 2 comma tilde, and I'm going to get this value right here. So the easiest way to represent the solution is to set x is equal to z tilde comma 0 and y is equal to z tilde comma 1, right? And those are going to be the 2 solutions. And then I could do plt plot t comma x. Let's do line width 3, and then let's call this color equal to red. And then plt plot t comma y, line width is equal to 3, color is equal to blue. We could also add labels if we wanted to. And then I can do plt show. And I run it and then kind of get a choppy solution. And the reason why it's choppy is because I'm only using 10 data points. So that's like 0, 1, 2, 3. And if I just bring this out to maybe 1,000 data points, now I get kind of the smooth solutions for kind of the oscillator, right? So here's kind of the x value, which we know is starting at 1, and the y value starting at 0. So x is starting at 1, and then we're getting kind of pure oscillations. Likewise, the y value, the blue curve, starting at 0, and then we're getting the pure oscillations. And we could run this as long as point. We could take this out to 50 time points, and then you're going to have a lot more oscillations. So that's kind of a pure oscillatory solution for this. The other way people represent this is sometimes they do this in a kind of what's known as a phase portrait. So let me comment this out. And what they do here, and let me change the solution. So let me make this a little bit different. So first of all, let me just put, for the second equation, minus 0.3 times y plus x. And if I look at that, I'm going to have kind of what's known as decaying oscillations or damped oscillations. Let's shorten this down maybe to 20. Right. And so again, we have the oscillations, but due to this negative term right here, basically the solutions are going to decay out. So often, sometimes what people do when they represent these solutions, rather than plotting x and y over here, so if I put my label, so my y label here is x and y, and then my x label is t, right? So I have my, what did I do? Oh, I forgot to put the PLT plot there, PLT. And so I have my x and my y solution, and then I go as a function of t, and they decay out. The other way to do this is, let me actually just come up to a new plot now, right here. So I could do PLT plot x comma y line width is equal to 3, and let's just make this color equal to black. Or let's make it green. And then my x label in this case is going to be x, and my PLT y label is going to be y. And then I can do PLT show. And I plot it up. And in this case, what we're going to have is, so here's the initial point. So this is the x value, which is 1. The y value is 0. And then we're going to have kind of spiraling circles is another way to represent this. So here we're plotting x and y. We're not showing time, but time is marching in this direction. And then eventually the solution will spiral in. And we probably want to do axis square. And so now we kind of have this square kind of diagonal kind of coming in. And then sometimes you might want to show the first point. So we could do PLT plot. And then we could just do x of 0, y of 0. And then maybe we'll put a circle there. And then let's do color is equal to red. And let's make it a little bit bigger. So line width is equal to 3. And now if I show this, here's the initial point, right? That's this one. So I'm plotting this, the initial point of x, the initial point of y. And that tells us the start position, and then we can see the spiral going through. So that's another way people typically represent, second order solutions, particularly if they have oscillations. So this is one way to view the solution. This is another way to solution. And this allows us to see how x and y covary with one another. Whereas in this case, we're seeing them covary as a function of time. So it's just a different way of representing the solution. So just coming back here, we can do more and more differential equations. We could do something like, A goes to B chemically, and then B goes to C. And maybe we'll assume the first rate is fast, and then the second rate is slow. And so if I'm going to write this function, right, so I have f of z comma t. Right, and then I'm going to unpack it. A, B, C is equal to Z. And then I could write out, A dot, in this case, is going to be minus A, right? So that would be the K1, or maybe I'll make this a little bit better. I can do K1, K2 is equal to 1 and 0.1. So I'm going to have minus K1 times A. And then if I write the differential equation for B, when A is being lost, it's making B. So I'm going to have K1A. And then in B, in turn, is going to go to C, so I'm going to have minus K2B, and then I have C dot is equal to K2 times B. And then I can return A dot, B dot, and C dot. And so that would be this kinetic system. Maybe my initial condition is 1, 0, 0. So I initially have 1 mole of A, and then none of B and C. I have my time span, which is MP Lin space, and let's try 10 seconds. I don't know exactly how long this is going to run. And then I could say Z, let me call this Z naught. And so I can just do OD int of F, Z naught, and T. And then my A is going to be Z tilde 0. My B is going to be Z tilde 1, which is the second column. And then my third solution is going to be Z tilde 2. And so this would be the first column, the second column, the third column. And then I can plot them up. So A line width 3, and then I could do color equals blue, and then PLT plot a T comma B, line width is equal to 3, and then I could do color is equal to red. Forgot the equal sign there. And then my last one would be PLT plot T comma C, line width is equal to 3, and then color is equal to green. And I forgot to make that red. And then I can do PLT show. Let's see if this works. And we have our solution here. So here's the A decaying, and then we're getting the B forming and then gradually decaying, and then the C component coming on. So maybe I'll want to run this for 20 seconds to get a little bit more clear solution. And this is kind of typically the kinetic pattern you would see for like A goes to B, B goes to C, right? So A here is going to B, which is peaking, and then B is gradually going to C, and we're seeing the slow decay of B and the large increase in C. So that's kind of just a brief overview of doing ordinary differential equations in Python. In general, I should say, if I come back to this code, most equations that we use, at least in chemical engineering, is they don't really have a right-hand side where it's time dependent. Typically, it's what we call autonomous. That's simply dependent on the state variables of the system, A, B, and C, but it's not going to have a time-dependent component. So I'll stop there. Again, if you have questions, put them in Piazza, put them in the comment section, and thank you.